Welcome back to this second morning session of today. And this talk will be given by Romeo de Cos from Sinvestav Mérida. And Romeo will talk about exploring the electronic structure of one-dimensional systems, a first principle approach.
Thank you very much, Mauro, for the introduction. And good morning, everybody. First of all, I want to acknowledge to the organizers of this nice meeting for inviting me, in particular for the opportunity to show some of our results from our group. And as you saw in my title, we are trying with one-dimensional systems. And just in this picture, you can see this kind of one-dimensional system. No, it's not exactly linear, but it's a low-dimensional. I am assuming that there are atoms, right? But I am not sure if in this institute is the idea, but in any way. Secondly, let me show the working group. And this is our group of students in Sinvestav Mérida. But in this project related with the porphyrin tapes, in general, nanostructures based on porphyrin molecules are working. These people, Miguel, Selene, and Aura, there are graduate students. And also Juan Hernández Tecorralco, he is around. He is a postdoc here in UNAM, in Institute of Physics. And also are collaborating an undergraduate student, OL, and the professor Néstor Valadez from the University of Chiapas. Before to start formally my talk, let me explain our vision about our contribution in this process of discovering new materials with interesting properties. As we can see in this picture, we consider that we have three important parts in the research: the experimental part, the theory, and the other one more recently after the computer's development, the modeling and simulation. In our case, we are in this part, obviously trying to connect with experiments and to understand theories to try to predict specific systems. And we use mostly ab initio methods because there are free of parameters and not require experimental data to this kind of simulation. Currently, in particular, the density functional theory is very well established to study this kind of system. So in this talk, I am presenting as an introduction and motivation some concepts about the low-dimensional materials, some problems, in fact, and secondly, a short overview about carbon nanotubes as an example of quantum liquid behavior materials. And in the next part, I am introducing the concepts for porphyrin tapes, in particular presenting the experimental results related with the synthesis and characterization. And in the fourth point, I am presenting our results of ab initio calculation related with the vibrational, mechanical, and electronic properties of these kind of systems. And finally, the conclusions and some remarks. Okay, low-dimensional materials are considered the materials that has effective dimensionality lower than 3D. For example, the two-dimensional materials like graphene, boron nitride, and others, decalcogenides, and all this new family that start a revolution in the materials science. Obviously, some of them are related with topological properties, another one with quantum properties. And in our vision, the next generation are the one-dimensional systems where the basic questions are what properties can be expected and what kind of applications also can be envisioned. So in our case, we are trying with one-dimensional systems at the atomic level. In this case, there are atomic chains or molecular chains in order to see the properties. So what can be expected when we are from the 3D to the one-dimensional systems? For example, for instance, we consider the Fermi electron gas model. In this case, the energy depends on the k squared, with the k is the quasi-momentum or the wave vector of the particles. Here on the bottom, I am showing the electronic density of states for each of these dimensionalities, assuming this model. And you can see that in the case of one-dimensional systems, we have a problem. Like the Houston, we have a problem. The problem is that, if you remember, if we integrate the density of a state, the area under the curve is the number of particles in the systems. But in the case of one-dimensional system, we have a divergence just here. Additionally, the energy of the systems is the integral of the product of the density of states times the energy. If we do this integral, also is diverging in this part. In this sense, the free electron gas model is not working in one dimension. To tackle this problem, many years ago, Tomonaga proposed to evolve from this system with this problem that I mentioned before to this dispersion relation, linear. He proposed this idea, and some years after, Luthinger improved this proposal, this model, and so on, and even Haldane also take this model to predict some properties that can be expected when the energy is depending linearly on K. In this model, the K parameter is this G that is related with the Fermi velocity, that is the slope of these lines, with the plasma velocity. The model depends only on this one parameter and is interpreted as the correlation between the particles. One interesting physics in this model, in these one-dimensional systems, is that the electron, when the electrons are moving, they are not really free as in the free electron model, because the motion of one of them is constrained by the other electrons, the other particles. So the only way to move is collectively. In this way, this is the plasma velocity. Okay, so this model is actually currently we call this the Tomonaga-Luthinger model, or just Luthinger model. And now we are moving to specific materials. One of the problems, additionally to this problem with the dispersion, energy dispersion relations, is the dimerization. When we have an atomic linear chain, as is in this cartoon, this picture, we have the problem that Professor showed in the last days of this conference, where we have an instability in this band structure, and after of the dimerization, this instability is removed, and we create a band gap. The first people working in this problem was the Peirce. This is in the very nice book of Quantum Theory of Solids. And after that, more recently, Michael Springborg also studied this problem for a particular carbon linear chain. And in this case, also we have this degeneration in this point of these two pi bands. And also the systems prefer the distortion, the dimerization, and creating this band gap. So in this way, from this very general point of view, never we can obtain a metallic system in one dimension, because every time is the dimerization is creating this band gap. This problem with more recent methods, more accurate methods like ab initio methods, was worked with this group in Turkey, and they obtained this size for the dimerization, the distortion, and this value for the gap using the GGA level for the exchange correlation potential in the density functional theory framework. So in our case, we try to propose some kind of mechanism to stabilize the atomic linear chains. And in 2010, we proposed that introducing the carbon chain inside of these carbon nanotubes, this linear carbon chain can be stabilized. Let me remember that in the case of carbon nanotubes, depending of the chirality or of this edge, we have a metallic behavior or semiconductor behavior. So in our case, we trade these two systems. Another additional problem with this simulation was the incommensurability, because the lattice parameter of the chains is not an integral number of the lattice parameter of the carbon nanotubes. So what was necessary to take a very large system with 1,000 of atoms to try to reduce the strain introduced for these constraints of the two different lattice parameters. Here I am presenting just a small part of this system, just to look. And let me discuss in more detail just one of these two systems, the metallic one. This is the system. In blue are the band structure for the system with no linear chain inside. It's just the carbon nanotubes. As we can see, here we have just at the Fermi level this linear behavior like the Tomonaga-Luttinger model. And also, if we introduce the linear carbon chain, this remains, but you can see that this slightly moved from the Fermi level, and this band is related with the red bands in this point with the linear chain. And also, the Fermi level is not used in the degenerated points. We interpreted, or we obtained information about this process, and the point is that the interaction between the chain and the carbon nanotube produce a small charge transfer from the nanotube to the atomic chain, the carbon chain, and stabilizing the regular chain inside the carbon nanotube. So from these results, we propose that this system can be a way to obtain these linear atomic chains, and in particular, to obtain this linear behavior like in the Luttinger model. More or less 6 years after this group, coordinated by Millie Dresselhaus, report the synthesis and the characterization of the carbon chain inside of these carbon nanotubes. The difference is that this is a multi-wallet carbon nanotube. And this is the Raman spectra of the structural characterization of these systems. And here we have a very well-defined the frequency of the Raman phonon related with the motion of the atoms in the carbon chain. Practically at the same time, also was reported another group, the same results, this multi-well carbon nanotube with the carbon inside, with this peak very well defined. So, in conclusion of this first part, we need to try to find conditions to stabilizing these linear chains, because in general are unstable. And in the particular case of the carbon atoms chains are very reactive, so it's not expected to be stable in room conditions. Now, with respect to just the carbon nanotubes, as I showed before here, just the carbon nanotubes has this linear relation here. It's like the Tomonaga-Luttinger model. And very recently, or more or less recently, this group from Berkeley has been reported the study of the plasmons, in these one-dimensional systems. This is the carbon nanotube image with the scanning electron microscopy, and this is the experimental configuration. This carbon nanotube is on top of this boron nitride, and using this voltage, gating voltage, they stop the carbon nanotubes. And after they apply a light in the infrared lights and measure with the STM tip the charge in the systems. With this kind of process, we can dope and move the Fermi level with respect to the Fermi Dirac point in any direction, depending of the sign of the bias, voltage bias. And there are very nice pictures of this experiment. You can see here the plasmons in an image. There are carbon nanotubes of different diameters, okay? And you can see here the plasma. But more than the image, the data, there are the data related. There are the image in one dimension, and you can obtain from here the wavelength of the plasmons and convert this in a velocity and plot this experimental data. And this equation is coming from the Luttinger model applied to the carbon nanotube. In this equation, we have this K parameter, and here is the Fermi velocity, here is the diameter of the carbon nanotubes, this is the wavelength of the plasma. Okay, all this equation fits very nice to this experimental data. So this is a conclusion that in carbon nanotubes, we have a quantum liquid, a Tomonaga-Luttinger liquid. From the same group, they try the same experiment, but now with a semiconducting carbon nanotubes. Let me explain briefly that the band structure of the semiconducting carbon nanotubes, the bands are not parabolic, are hyperbolic, following this kind of relationship, okay? In this case, the energy gap of these carbon nanotubes, it depends on the diameter of the carbon nanotubes, and they apply the same technique that in the before experiment, and they obtain also this kind of image with the presenting the plasmons, and with the gating can be doped the system and shift the Fermi level. In this case, this is the experimental plot for the plasmon wavelengths, and the red line is the nonlinear version of the Luthinger theory. The nonlinear version means that in the Luthinger model, we have the perfect linear relation, and the nonlinear means that we have this hyperbolic behavior around the Fermi level. So these two experimental reports, in my opinion, are the best demonstration, evidence of the Luthinger liquids in any one-dimensional materials, in this particular case, in the carbon nanotubes. So now I am moving to the systems that we are proposing to study based on porphyrin molecules. Sorry. And let me start presenting the molecule. This is a free-base porphyrins. The gray are carbon, the white are hydrogens, and the blue one are nitrogen. And this molecule is very, very interesting because can be accepted or can be put here practically any metal atom inside. In this case, when the systems contains a metal atom, we call metalloporphyrins. Metalloporphyrins are very important in biochemistry, in biology in general, because starting from this molecule, you can attach, or the nature attach different molecules in the external part, and as mentioned before, also we can change the metals, and the function of the molecule is changing. It's not the main topic of the talk, but for me it's very exciting that in many aspects of our life, the porphyrins are inside. In particular, in our blood, the core of the globulin is just a porphyrin with iron in the center. The chlorophyll is also a porphyrin with a magnesium in the inside. All the nervous systems, all also porphyrins with cobalt inside. And in fact, one of the oldest bacteria, the archaea, are based, they are the very primary life systems in the world, are based also on porphyrins. In this case, has nickel inside. So you can see that this molecule is very flexible and very abundant. So our idea is to think this molecule as a building block and ensembling this one to produce these one-dimensional nanostructures or tapes, as in the literature we call. And interestingly, from the experimental point of view, this group, from Japanese group, reports in 2001 this, the production of these kind of systems. In this case, when this is planar, they call tape. When the link is orthogonal, they call chains. In this case, are based on the zinc porphyrin, and has been obtained for the largest one was 12 units in both configurations, chains and tapes. So this experimental report is our main motivation to study this kind of systems, and we start calculating all the properties, basic properties for the tape based on the free porphyrin, base porphyrin, and the magnesium and the zinc as a way to change, to evolve the metal and to see how the properties are evolving. In this case, we don't have metals. In this case, we have a metal with the s electrons at the valence, and in this case, also s electron, but with d electrons very close to the Fermi level. All these calculations were performed using the density functional theory as embodied in the siesta code. You can see here the computational parameters, and if you are interested in the details, we can discuss in more detail after. Here, when we are trying to propose a new material from the computational point of view, we need to check different aspects, starting from the stability of the system, the mechanical properties, the vibrational properties, and obviously the electronic properties. In this case, just an example, here are the phonon band structure for the zinc porphyrin tape. You can see here that all the frequencies are positive, are real. So that means that the system is stable, vibrationally stable. And this is the stress-strain curve. And also we can obtain from here, from the linear part of this curve, we can obtain the Young modulus. And this is the value for this system. And this is the value for the graphene nanoribbon of the similar size, weight. As we can see, is more or less the half of for graphene. So that means that this system is stable and has robust mechanical properties. That means that it's a viable system. Okay, now moving to the electronic band structure. There are the electronic band structure for the three systems. Here we can obtain in red the band structure obtained with the PBE at the GGA level for the exchange correlation potential in the theory. As we know, this exchange correlation functional underestimate the band gap. For that reason, it's necessary to go a higher level of theory. In this case, we use this hybrid functional that improve the prediction of the band gap. There are in blue. And nicely, we can see how this small band gap is reducing as we go from this system to the zinc porphyrin system. Let me show these plots in this part, in the lower energy part. Here we have in the lower energy part, and these one has a very small gap, and in the zinc porphyrin is practically zero. In any case, we have a hyperbolic behavior. Here are the numbers for the different systems and the different functionals. You can see here that are very small. But in order to obtain the Fermi velocity and the mass associated to these particles, we use a massive Dirac Hamiltonian. From that, we obtain this hyperbolic relation for the energy as a function of k. And we fit this equation to the ab initio calculation in order to obtain the mass and the Fermi velocity of this system. You can see here the values are in the same order that the Dirac fermions in graphene, but in this case we have a very small mass. It's not exactly zero like in graphene. So in this way we can see that the electrons in this kind of porphyrin tapes are massive Dirac fermion, has massive Dirac fermion behavior. Okay. In order to have more information about this kind of behavior for these particles, also we study finite systems, starting from the monomer to the type with 12 units. We have calculated the electronic structure for all these systems. And here are the value of the energy gap. Let me focus on the hybrid values, the blue one. And the others symbols are experimental data coming from different techniques, experimental techniques to measure the band gap. And our feeling about this difference is that is depending on the effect of the substrate during the experiment, because in the voltammetric method, they put the chain in size on top of a substrate. And additionally, our systems, we have considered a perfect, and in the experimental case has some impurities in the edge of this system. In any case, we have a very nice behavior. The band gap is decreasing as a function of the size. And in order to interpret this behavior, we start with the simplest, probably the simplest model of a particle in a box. And let me remember that if you solve this problem using the Schrödinger equation, you obtain the separation of the energy states of the eigenvalues is depending on L1 on L squared. But if you solve the Dirac equation for this problem, that is in different books and papers, the gap between the eigenstates is depending on 1 on L. So we have a very different scaling rule for the energy gap, depending for Schrödinger equation or Dirac particles. So we try to fit these two models with this kind of scaling rule. And in black is the Schrödinger version. As you can see, don't fit to the calculated values. And in the red is just the 1 over L. And in blue, in this case, we don't fix the power of the L. We are free to fit. But however, it's very close to 1. It's not exactly 1, but it's close to 1. You can see that you can obtain the number of 1 using the simple model. This is a real system, but it's clear that it's very close to 1. So this is, in our opinion, an additional signature that the particles in these porphyrin tapes are Dirac particles. So in summary, we can say that The zinc porphyrin tapes shows dynamical stability and robust mechanical properties. We find that the band gap decrease from the free-based porphyrin systems to the zinc. And more interestingly, the electronic structure shows that the behavior of the particles are like the massive Dirac fermions, and also the scaling rule for the energy gap is consistent with this interpretation. So from this point of view, we propose that the zinc porphyrin tapes is a strong candidate to show Tomonaga-Luttinger behavior. Some open problems or future problems to study in these systems. One of them is, for example, the effect of a substrate to try to calculate these porphyrin tapes on top of different kind of substrates. The other one is the thermal stability to study the system using, for example, the molecular dynamics to see how much is stable with the temperature, because all these calculations are at the ground state, at the zero temperature. And probably more interesting for this group, for this audience, is to ask if this kind of system are topological material or not. So in this way, we are open to discuss and eventually to collaborate to try to see if this kind of systems can be topological materials. Thank you for your attention.
Okay, thank you very much, Romeo. Are there questions? Please.
Yeah. Well, you were showing like this parabolic semiconductors, like
Hyperbolic.
sorry, hyperbolic dispersions. Like there seems some signatures of some charge density, but I don't know if it's like some density waves. Is this charge or spin waves somewhere in
Okay,
your system?
It's important to mention that one of the results of the theoretical derivation from the Tomonaga-Luttinger model or theory is that you obtain that the solution is separation of charge and spin. This is a very old standing problem in the experimental part, because we don't have any evidence in any material of this kind of separation. This is a very active, this is a very active of research from the experimental part to try to see, to detect this charge separation. But in the case of the carbon nanotubes, these plasmons that you are appreciating in this is just charge waves, charge density waves. Yeah.
Thank you very much for the nice talk. I have a question for when you go from 3 dimensions to 2, for example, in case of graphene, let's suppose you have these flexural modes, and I saw that you calculated the phonon.
For graphene?
No, for this one. Yeah, because I was wondering if there's something special, because if there are like, for example, you have a rod, you can have like these figures, because you have this bending of the rods, and so I was wondering if there's something special in that part of the spectrum for the phonons.
Let me explain before to respond. The main question is from the theoretical point of view or simulation point of view. In the case of two-dimensional systems, any two-dimensional system or one-dimensional system, is that it's very hard to converge this part of the band structure. For example, if you use a very few Q points in the phonon calculation, you obtain a band that cross zero. This is the negative or imaginary frequencies, and that means it's stable. However, if you improve your calculation, you can obtain this. It's anomalous because it's not linear. It's parabolic, the acoustic phonons in this system, like in graphene. Okay. So you can expect some kind of anomalous properties in the vibrational part, or even in the thermal part, yes.
Okay, so maybe our last question.
Hi, nice talk. Interesting systems. I thought that Porfirio was not allowed in Mexico. But,
Yeah.
well, that was a joke part. But okay, about separation of spin and charge.
Yeah.
A manifestation of that is that the collective mode for charge and for spin is usually very different, mostly because of Coulomb effects. And the difference can be factors of 5, of 10 in the velocity of the spin fluctuations versus the charge fluctuations. So the only way to measure that is to measure that, is to see that. So one can do that with spin polarized STMs. So we inject electrons which are polarized, it has spin polarization,
Yeah.
and you have an impurity or an edge or a boundary. You then have a photoemission experiment, if you wish, but in the way that is actually spin dependent.
Yes.
So that is the only way to actually detect this.
Yes, yes, I agree, of course.
Because to do neutron scattering is
Yes.
impossible in one
Yes,
dimension.
but the problem is that the people has tried in this one-dimensional systems like carbon tubes, the other one, but they don't find this.
But do they go to the very low? Most of the STM experiments in nanotubes are done at room temperature.
Yeah.
And you have to go to very low temperature to see
Yes,
this.
even at low temperature.
Because the spin, usually what happens, the spin part becomes incoherent. People have shown that
Yeah.
the temperature is not too low, it's only the charge part that is coherent, and the spin part is incoherent.
Yeah.
So it may be hard to detect because of that.
Yes. Okay. Probably. But returning to the joke of Porfirio, the two-dimensional version of this system, if you attach more molecules in the vertical direction, you can construct a two-dimensional. The name of this system is Porfireno. Yes, this is the official name, right? not the nickname, it's the official name. Porphyrin, yes, porphyrin, like graphene, but based on porphyrin is porphyrin, yes. In Spanish it's porfireno, like Porfirio. Okay.
Okay, so if there are no more questions, we thank Romeo again. Thank you very much.
La corona. El cetro.
¿Acá? ¿En la blusa? Sí, sí, en la blusa. Ok. Sí, porque si pones en las dos, pues... Ah, ya, entendí, claro. Ahí. Ahí. Sí. Ya quedó. Bueno. Perdón.
So our next speaker is Rosario Paredes from the Instituto de Física. And Rosario will give a talk on topological phases in spinor dipolar condensates.
Thank you very much, Mauro, for the introduction. I want to thank to the organizers for inviting me to this workshop. It is a pleasure to be here. Yesterday and today we have heard about different manifestations of topological states of matter, and mostly in condensed matter. As said by Professor Fradkin, these phases are beyond the classification of Landau for phase transitions because they are not characterized by having an order parameter. And what you will see in this talk is another system, another kind of systems which also have topological phases. I'm referring to skyrmions in dipolar Bose-Einstein condensates. For this purpose, first, I will give you a very brief introduction about what is a Bose-Einstein condensate, just to remind the textbook concept, and then what is a Bose-Einstein condensate in real life, I mean the Bose-Einstein condensates that are produced in the laboratory, and then I will tell you about the similarities that share both the ultra-cold matter and condensed matter system, and this is why this is not a surprise that also these topological phases can exist in Bose-Einstein condensates. So I will emphasize the characteristic that this system shares. Then I will go to the main point of this talk, which is how we can describe these topological phases, in particular in dipolar condensates composed of three spinor components. This refers to these phases of a dipolar Bose-Einstein condensates. Through the so-called famous Gross-Pitayevsky equation, this is the mean field approach, to precisely talk about the emergence of this ischemia, which is the spin of the spin coupling, and then you will see how dipolar Bose-Einstein condensates. Einstein occupation of the box of volume B at temperature T when the chemical potential goes to 0, and then this is why when particles go to the ground state, they had no cost of occupying this state. You see of different of a sequence for the onset of a Bose-Einstein condensation. So this each of these curves of this plot corresponds to different temperatures. As the temperature is lower to nanokelvin, the appears signature of the Bose-Einstein condensation. So in a laboratory, these systems are produced in neutral, in particular were produced in alkaline atoms, neutral alkaline atoms like lithium, sodium, potassium, and rubidium. Laboratories to produce these condensates are these two, laser curing and evaporative curing, which allows the experimentalists to go from room temperature to these nanokelvin temperatures. So important in the real Bose is that they have interacted the main against the original Bose condensate, I mean the Bose condensate of the textbook. So the interaction is the main. There is another ingredient that is on a present, and this ingredient is the presence of a harmonic confinement. And because it's possible to produce condensates in a box, but instead of in a box, so the condensates are produced in a harmonic potential. So then a real Beck is a weakly interacting superfluid. And this, and also related with the dimension of condensates, the real condensates exist. So the dimension can be controlled by varying harmonic. It's possible to have condensates in 3 dimensions, 2 dimensions, like having a disc-shaped condensate, and also when the frequencies are also varied, the frequency along the 0 direction is very different against the frequency in the y and x direction. Then it is possible to get a cigar-shaped condensate that is a kind of condensate in 1 dimension. So the other ingredient, very important as I told you, are the interactions. So, no, let me skip this. So the other ingredient is the interactions that are present in the condensates. So the interactions can be either short range or long range, and are shown, they are shown short range if the atoms are alkaline atoms, but if the atoms are other atoms like, for instance, strontium, rubidium, strontium, chromium, erbium, in that case, so there exists a high magnetic moment, and in that case, long-range interaction cannot be neglected. In such a case, to describe these systems, one must include both the contact interaction and also long-range interactions, so as dictated by the standard textbook in electrodynamics. So the interactions, the short-range interactions, comes from the internal structure of the atom, and these are these are the line, the curve, the red curve correspond to the real interaction between neutral atoms, which is composed by 2 parts, a repulsive one and an attractive one. Then when you sum these 2 blue curves, you get this red curve. And what about the long-range interactions? So this is the usual, the standard formula to take into account 2 atoms having a dipole moment M1 and M2. And the important thing in this slide is to mention that the quantity, there are 2 quantities that characterizes the interactions. While this constant, this coupling constant GC characterizes the contact interactions, which are the short-range ones, and the other quantity is this GD, which characterizes the dipole-dipole interactions. It's very important to take into account these long-range interactions because it gives rise to different phases in real superfluids. These phases are, for instance, droplets and solid phases. In this slide, I'm summarizing the main characteristics that share the systems belonging to either condensed matter and ultra-cold matter regime. So, as you know, each follow the Fermi-Dirac statistics. I'm talking about electrons, and in this case, you can have both statistics. So I didn't tell you, but the first realization of the generate Fermi gas happened in 1999. It is also possible to confine these ultra-cold gases in optical lattices, which mimics the same thing that that electrons confine in ions, that is the solids. But also, it is important to say that the very different temperatures have these systems to be in the degenerate regime. So both of these systems exhibit vortices in presence of a magnetic field, and in the case of ultra-cold matter, the experimentalists have been observed the emergence of vortices. At the bottom, you can see very different phases that can be seen both in electrons, obviously, and also in ultra-cold matter, these so-called ultra-cold quantum fluids. And how to describe, before telling you how to describe these systems, just let me tell you that very recently, last year, it was possible to realize, to produce, a dipolar Bose-Einstein condensate composed of molecules of cesium and sodium. And this is and again, this snapshot corresponds to the onset of the condensation. But even more, it is possible to add an external magnetic field to this system. And why an external magnetic field? Because it is a matter to synchronize the interaction between these dipoles. What you see in these equations is that the effective interaction when two dipoles are in presence of an external magnetic field, so the effective interaction takes this form. So you can see here a contact term and also an additional term that becomes a convolution term. This is why I will tell you in a few minutes. But the important thing here is to emphasize that the dipole-dipole interaction can have repulsive or can be effectively repulsive or attractive because the condensate is in presence of an external magnetic field like this one. And how to describe these systems? So these systems can be described by the famous Gross-Pitayevsky equation. Independently, Gross in England and Pitayevsky in Russia derived the Gross-Pitayevsky equation to demonstrate the existence of vortices in superfluids, and also in the case of vortices, the famous Abrikosov lattice of vortices in superconductors in presence of a magnetic field. So this Gross-Pitayevsky equation allows us to explore so many different phenomena in ultra-cold quantum fluids. What you can see here is these examples of these phenomena. For instance, topological phases, as we will see in a moment, and quantum turbulence. Also, it is possible to include finite temperature effects in this equation, multipolar order phases, liquid crystals, droplets, as I told you, and quantum magnetism. And in order that this phenomena can be predicted by through the Gross-Pitayevsky equation, what one have to add is different terms. So what are these terms? For instance, here you can see these long-range interactions, I mean the dipole-dipole interactions, and also it is possible to add this well-known Li-Wang-Yang term, and also instead of having the wave function of the Bose-Einstein condensate, you can replace this wave function by a spinor wave function. And also you can control the geometry, and as I told you, the geometry can be controlled by means of the external frequency in these condensates. Very recently, with my student, Cristian Madroñero, we studied the phases that appear in a mixture of a Bose-Einstein condensate, of a dipolar Bose-Einstein condensate, confined in one dimension in 3 different potentials. So we use specific parameters associated to real atoms. These atoms are erbium and dysprosium. And so it's very hard to solve this equation, perhaps I must say that, because, and why it's very hard? Because as you can see, when you include these dipole-dipole interactions, the generalized Gross-Pitayevsky equation acquires this convolution term, so it is very hard to solve this equation. but it is possible, of course. And the red and blue arrows represent the two components of the system. And here, so the external potential corresponds to the one-dimensional harmonic potential, also to a lattice to an optical lattice, or to a box. And why we're interested in very different external potentials? Because, as you know, in real solids, we don't have harmonic potentials, but instead of that, we have potentials like a box potential. And this is why our interest in solving this kind of considering this kind of external potential. So the results are summarized here of this paper that actually was published today. So what you can see, depending on the external potential, so you see on the top of this table the case when the external potential is a lattice, or is a homogeneous or box, or a harmonic one. So depending on the parameters, what you can see is the formation of droplets like this one patterns. That means that the condensate is tightly confined in a region of the space. But also you can see that phases can be occupying the same place, which means that erbium and dysprosium atoms are mixed, appear in the same place. Or you can also see droplets, but separated, depending on the parameters that we use in the Gross-Pitayevsky equation. And also you can appreciate the form of the potential, because in the case of the lattice, the density of the particles, which is the quantity that we are plotting here, here is the density of erbium and dysprosium atoms. It is possible then to see separated or mixed phases, as I told you, depending on the values of the parameters. What is A11, A12, and so on? It represents, I will go to the previous slide. Oh. So is this quantity, the S-wave scattering length, which can be varied externally in the experiments, in real experiments. And as I told you, also the magnetic field is a quantity that can be varied in the experiments. So this is why so the predictions of our results reproduces states like this one. So this is the real photographs of a dipolar mixture of a condensate in 2 dimensions. And so the whole phase diagram, which you can appreciate here, the whole phase diagram for the system. And as I told you, depends on the values of the parameters. So you can see the frontiers that separates phase separated case when the erbium and dysprosium does not occupy the same region. And also, you can see here in this dark blue, when the two species are separated, and these plots correspond to so the numbers here, 1 and 2 and 3 and so on, correspond to the previous phases I showed you in this plot. So then 1 corresponds to the regime of droplets, that is separate droplets, or separate droplets in a homogeneous case, or separate droplets in the harmonic case, and so on. So this phase diagram summarizes the whole the whole phases that can be seen in this dipolar mixture. And then where else? So let me tell you that, so to obtain this phase diagram, the important thing was the design of the specific observables to measure where we can find droplets, mixed state or separated states. These observables are here. So this is the phase separation observable, and this is the droplet observable. So we designed this according with the experiments, precisely. And then what is our motivation and what is connected with this workshop regarding this work? So as I told you, all of these, so this phase diagram corresponds to dipolar Bose-Einstein condensates in one dimension in different external potential. But now, connected in close connection with this workshop, so how we can add some other elements to the Gross-Pitayevsky equation to study topological phases. The answer is that, again, we look at for a parallelism in condensed matter. So what is the parallelism? The existence of skyrmions in condensed matter. You can see here a work from 2010, and the upper snapshot correspond to computer simulations, and in the bottom you see the experimentally for this compound. And what you can see here is the formation of a skyrmion. And what is a skyrmion? So a skyrmion is a real vector in a space which shows topological defects, exactly like the vortices in the Bose-Einstein condensates. So in fact, vortices are a kind of skyrmions. And why? Because at the origin, the density goes to zero, is zero exactly, and then this is why this is a topological defect in the density. And how skyrmions can be seen in Bose-Einstein condensates, so in these degenerate states of matter. So the answer is here. So there are several ingredients that we have to add to the Gross-Pitayevsky equation in order that skyrmions in ultra-cold matter can be appreciated. So these ingredients are, so first, we need to have, so there are several ways. One is by adding a magnetic field with certain points in which the magnetic field is zero, but the other way is by means of adding a term, this spin-orbit coupling term. But also the necessary, indispensable condition is to consider the spin-orbit interaction most and this spin-orbit ingredient and generalized gross statement summarizes what a system that it is possible to realize in experiments, and you can ask what is the origin of the spin-orbit coupling in Bose-Einstein condensates. So the origin is related, is indeed an artificial gauge field. And how it comes from? It comes from the, in the next slide you will see how it comes from. So it is precisely related with the presence of different spinor components. This work is in progress. Sorry, I will not present a complete result, but this is a work in progress. And this is the equation that we are solving. So, although it seems like very complicated equation, is indeed can recognize the terms previous show you in the previous equation. Let me show you why. So what you can see here is the kinetic energy. So remember that nu is the index to distinguish the different hyperfine spin components. And this is the which can be whatever, a box or a lattice or a harmonic potential. So we are studying condensates in 2 dimensions. This is the spin-orbit coupling, and this is the term, the effective term. And you can see here the terms associated with contact interactions among components. So each time that you see this G with a super C refers to the contact interaction. And then you can also see this GD. This means the dipolar interaction. The dipolar interaction captures also a part of contact interaction plus a convolution term. And what are the results after solving this equation for the stationary states? So the results are, of course, the density, the wave function of the different spin components. And what is the spin texture? And this is precisely the quantity in which these topological phases manifest. So the spin texture is the expectation value, the normalized expectation value of the magnetization. And if you, when we can see an skyrmion, if you, so this quantity F is, as I told you, this normalized. The component along Z becomes 0. No, not becomes 0, but points in a positive or negative direction of Z-axis, and the perpendicular components become 0, then show you in the next slides the results. So of skyrmions seen in this spin and condensate with that. It's not easy to see here, but these regions correspond precisely to points in which it is satisfied this condition that the perpendicular component of the magnetization becomes 0 in the X-way space, and either positive negative direction of Z. Yes? Yes, exactly. It's the whole texture. Yeah.
Okay, but you're saying that the in-plane component goes to 0. So I would think that the spin has to kind of continuously kind of wind.
Perhaps you can see here some arrows.
Yeah.
Huh? So the arrows are the arrows are pointing in the 3-dimensional space, and there are some regions in which the arrows are 0 in the X-way space, and they point to the positive or to the negative.
That's kind of the nucleation.
Yes, exactly. Okay. So each time that you see regions, what you are finding is a skyrmion. So we solved the equation for several potentials, so including lattices in 2 dimensions with different geometries. For instance, here the first one corresponds to an homogeneous potential without a lattice, and here this is the result when you include an hexagonal lattice, or a triangular, or a square lattice. And in the other slide, also one can find a kind of self-similarity effect in this for the stationary state of the spin texture. And what else? So remember that, as mentioned by Professor Fratkin, so there are several quantities that that are a signature that allows you to conclude that indeed a topological phase is present. And what is the signature in this case? So the topological charge. So originally this topological charge is given by this formula, and so remember that this quantity F is the texture, which is a quantity defined in the 3-dimensional space. This actually I didn't. Oops. I don't remember now the of the H bar. I'm so sorry, but the important thing is that QS belongs to the integers. So how to calculate or to determine this topological charge in Bose-Einstein condensate? Very recently, my colleague Victor Romero Rochin and collaborators derived a general formula for the chiral charge, which is this formula. As you can see, this formula has 3 terms. So the first one corresponds exactly to this one. The other terms, because in particular in our case, the condensates are complex objects in which the frontier is not well defined, because remember that we are using a harmonic potential confinement, and also because you don't know where exactly the skyrmions can appear. So then you need to have a formula to calculate this topological charge. In this case, so this general formula is precisely this one that includes besides this another term that associated with the contour of this frontier, and so the contour can be arbitrary, and the boundary also is arbitrary. So this formula is for a general boundary and contour, disregarding the existence of these corners. So in fact, when this corner exists, then this term precisely corresponds to the existence of these corners. In this way, what you can find is that always this number is an integer number. So they demonstrate this in this article. Yes?
In principle, the topological charge is the quantity on top.
Yes.
Okay, now you're trying to do this for a lattice of skyrmions, is that the issue?
This is the general formula as you.
The formula that gives you the topological
Yes.
charge for skyrmion.
Yes.
But
Yes.
if you have a lattice of skyrmions, that formula is not useful.
That formula is incomplete in the sense that when this formula applies just when this quantity vanishes at infinite, f, when the spin texture vanishes at the frontiers.
It has to be the same value, it doesn't have to vanish.
Excuse me?
It doesn't have to vanish, it has to point in some arbitrary.
Yeah, the spin texture points in arbitrary, yeah. In that case, the general formula that, so this.
F doesn't, for the top formula, F doesn't vanish anywhere. F is actually
I mean, in our case, it occurs that, that in some cases it doesn't work. And why? Because what you find is that this chiral charge is fractional, for instance. And in that sense, so you need to add some other terms. So this was demonstrated in this work. This is what I'm saying. Yes?
So the formula on top applies to, it's like a Gauss-Bonnet theorem.
Yes, exactly.
On a closed surface.
Yes.
And then the second one applies to an open surface. The boundary term gives you the contribution from the surface on the case of an open surface. But I also have a question on the last term because I have not seen it. You are saying that if there are kinks on the surface,
Yes, when you have these corners.
that part.
Yes, you have to add that part. In that case, you get always integer chiral charge.
So, okay. So
This is the condition.
yeah, so just to connect to what Eduardo was saying, because I think that he's asking if the last term is needed, because in reality you don't have a continuum, but a lattice.
Yes, so we have a lattice. So we can have a lattice or a.
She has a lattice of skirming.
Yes.
Which
Oh,
are-
I see. Okay.
Okay, and I think that's part of the problem.
There is a lattice of skirmions, of course, and also one can have a lattice because of the external potential.
Yeah, but skirmings are big compared to the lattice spacing.
Yes, exactly. So in the next slide, in the next slide, I'm summarizing the results found up to now. So first, so our aim is to classify these skirmions that appear in dipolar Bose-Einstein condensates. So what we have found up to now is that you always need to have phase separation. Just in the regime of phase separation, then we have to choose the proper parameters in which this spinor condensate is phase separated. And then when dipolar interactions are included or not, so this means that they are not included, and this means that they are included. So the dipole-dipole interactions can be attractive or repulsive. And also what happens with the spin-orbit coupling is included. And in that case, what we get is that skirmions can exist or not, and the type of skirmions that we can get. For attractive dipolar interaction, symmetric skirmions with respect to the origin are always formed for small spin-orbit coupling, while for large spin-orbit coupling, a skirmion lattice is formed, like a staggered lattice of skirmions. So skirmions pointing in the in the positive direction, and skirmions pointing in the negative direction. And with this, I want to thank and finish. So thank you very much. Yes.
In magnetic systems that have skirmions, for instance, or even those that don't have it, if you have spin-orbit interaction, there is a called magnetic. That means that exchange interaction, say, between the magnetic moments is actually not isotropic anymore. When you include that in systems of this type or others that have skirmions, What happens is that that breaks the symmetry, the SO3 symmetry that you expect to have, down to a U1 symmetry or Z2, depending on the size, the sign of this magnetic anisotropy. When you have something that prefers to have what I call easy plane interactions, where essentially the skyrmion essentially likes to be flat on the plane, instead of skyrmions, you get merons, which are half. Merons in the usual SO3 case are very expensive. They have a linearly divergent energy. But in this case, actually, they become logarithmic, and they are effectively the same as a vortex. So I was wondering, in your case, since you actually have spin-orbit coupling, if what you're seeing are actually not merons instead of skyrmions.
Perhaps we should
And merons
explore.
actually have half of the topological charge.
Okay.
Okay.
So we are exploring right now.
Right.
So, but
In your equations, it was hard to determine,
what's
for
up?
me, what the role of the spin-orbit interaction is, but I would a priori assume that it will actually produce merons
Okay.
or domain walls, depending on the sign of the anisotropy.
Yeah, perhaps these domain walls are like these regions separating the skyrmions.
Yeah, because it depends on the sign of the effective magnetic anisotropy. I mean, you can derive an effective nonlinear sigma model to study this, okay?
Okay.
And the nonlinear sigma model can have an extra term that gives you this uniaxial anisotropy or E-plane anisotropy. And people have done this in dipolar, actually in spinor condensates also, and in other, but also in systems, in magnetic systems and so on.
Okay. So thank you very much.
Babak, you were, no?
Yeah.
Other
It was very nice, your talk, and congratulations for your paper. And related to that first part of your talk, you mentioned that you produce a phase diagram. I was wondering how stable is this phase diagram, for instance, on the external fields?
This phase diagram.
That's right.
How stable is? So the Gross-Pitayevsky is solved with using the imaginary time evolution method. So the normalization of the wave function is tested. And we always, to ensure that indeed correspond to a stable phase, each result is put to evolve in a time. And then what you get is that the system belongs in the same place where the initial condition. And then this is why we conclude that it's very stable. So.
Okay. And if another short question.
Yes.
You mentioned in one of your slides that in the spin orbit appears the gauge field.
Yes.
Can you show us where the gauge field, please?
Yeah. Perhaps to tell you. No, sorry. So you say here, why this spin orbit coupling is an artificial gauge field in the case of Bose condensate? Because this artificial gauge is produced by the spin, by the existence of different spin components. So you don't need any external field. It's true that another way of producing these skyrmions by adding an external magnetic field. And in that case, you also will have a kind of magnetization in the system. Holes that is. So this is the artificial gauge because it's the result, simply because you have a spinor system. Thank you.
Okay, so we thank Rosario again. Yes. And our next speaker is Igor Shovkovy from Arizona State University. And I will wait for the title to come up.
Start it? Yes, it's good.
This one?
Two, yeah. No, part two.
Ah.
This one. The very last, yeah. Okay.
So go ahead, Igor, with your second part of your talk.
I know that I'm the only thing standing between you and the launch, so I'll try to be as efficient as I can. So today I was planning actually to start with the Dirac and Weil semimetals, but there is a very small piece that is left from the high energy physics from heavy ion collisions, and I would like to briefly talk about so that I will be on time. As I was telling you previously, there are different probes of heavy ion physics, and we were trying to find some observables that tell us something about the chiral magnetic effects. And unfortunately, many of those observables, they didn't really didn't get realized yet, because in fact those are difficult measurements of parity even observables, and I should emphasize on that, which are trying to detect something about parity odd physics, pretty much where the problem lies. There is a lot of background coming from the effects. As a result, you are becoming unsuccessful. Well, in principle, you could actually develop some other observables, and those would be parity odd. And this is a very brief sketch of a proposal that was essentially just put out in 2024 by me and my former student. And we were proposing to look more closely at the electromagnetic probes, in particular the photon emission from quark-gluon plasma in the presence of a strong magnetic field. You could formalize the calculation. You know how to calculate the emission of the photons, and this is just the formula. I don't want to go into details. What is important that essentially it's very, very basic processes that you are really calculating, but there is a way of doing that very efficiently through calculating the imaginary part of the polarization tensor and so on. The most important thing is that these processes are the processes that exist only in the presence of magnetic field. You probably would immediately appreciate that if you have this process is happening in vacuum, then energy and momentum conservation will tell you that those are impossible. In the presence of magnetic field, this is very straightforward. In fact, you could think of some of them actually as a synchrotron radiation. The others are just annihilation of quark and anti-quark, but in a strong magnetic field producing a single photon, not two photons. Anyway, with that little introduction, I just wanted to say that what are those parity odd observables? And in fact, those are essentially the emission of the photons, and this R represents the differential rate for the photon emission, and I removed all because obviously we don't have time for that, and put just plus and minus there. Represents the emission of the photons with circular polarizations, positive, negative circular polarization, clockwise, anti-clockwise, whatever you define it. The bottom line is that you could create these observables where you consider the differential emission rate of circularly polarized photons with one circular polarization and find the difference, and then you could divide by the sum so that you could get the unitless quantity that measures the degree of the polarization in your emission. And of course, here there is something else, this angle phi, which is essentially measured from the reaction plane. So if something goes up, phi is positive. If something goes down, phi is negative. And basically, it's a quantity that you could characterize for any direction. You could also try to consider something as a spatial asymmetry in that circular polarization. And of course, you could consider separately the characteristics for one and circular polarization. And in this case, you could see that I'm considering one positive circular polarization, but I am comparing the emission in the directions plus and minus phi. So essentially, it's reaction symmetry with respect to the reaction plane. So if something goes more in the positive direction, this will be a positive quantity. If something goes in the negative direction, it's a negative quantity. And what this basically tells you is a spatial asymmetry of that circularly polarized light. Now, if you do the calculation for that emission, and of course, that can be done. In fact, it can be written down to essentially an analytic formula for that calculation, with the only subtlety that there will be a very large sum you have to calculate, basically considering all possible transitions between all possible and you will see that the two different characteristics. For one polarization, it's the solid lines going in the positive direction. For the other polarization, it's a dashed line going in the negative direction. And this immediately tells you basically everything you need to know. It basically tells you that if you have different types of charges in the system, the electrical charge chemical potential or the chiral charge chemical potential, you will have these characteristics that are basically showing that there is spatial asymmetry in the emission, and also there is an asymmetry between the polarization with positive and negative circular polarization, because those values are larger and smaller. So the overall ratio is controlled by mu. The positive negative is controlled by mu5. And essentially what that tells you that you could really get a very easy qualitative understanding of that system by simply considering those observables. If you have non-zero electrical charge density present, you will find that one circular polarization dominates over the other, which is of course not super surprising. This is essentially, if you wish to put it that way, a photon version of the Hall effect. And the idea is very simple. If you have a certain charge density present, then basically circulation of those currents will be in one direction, and that produces, of course, one circular polarization higher than the other. So that's very straightforward. If you have non-zero chiral charge density present in the system, it's a little more subtle, but of course this is a parity-odd quantity, and it produces parity-odd observable. In fact, if you look at the emission of the left-handed polarization, then you will see that it has higher emission in the direction opposite to the magnetic field. If you consider the other polarization, it's stronger in the direction of the magnetic field. And if you were able to see that in heavy ion collisions, then pretty much you will be able to tell that there is a magnetic field in the first place, because these processes are essentially triggered by the magnetic field. But also comparing the different types of asymmetries, you will be able also to tell what kind of content that plasma has, what kind of charges it has present. So that's very beautiful theoretical side, and pretty much I'm going to stop here because there is no experiment for this, and probably it's not coming soon yet because unfortunately it's very, very difficult. Not impossible, but very difficult. And I should say we only proposed this last year. Anyway, that is pretty much all I wanted to finish on the heavy ion collisions. And the bigger message that I was trying to carry here is to tell you that there are very, very interesting elements of physics that we were trying to probe in heavy ion physics that are related to chiral anomaly, chiral types of matter, and all those interesting things. The negative thing about that is, unfortunately, the observables are extremely difficult to extract from heavy ion observables, and therefore if you really want to make sure that we are at least going on the right path without thinking about some physics that doesn't exist, maybe there are actually ways of testing it somewhere else, in particular in the context of Dirac and Weil semimetals. And of course, those are very, very different systems. And here is sort of qualitative understanding. This is a very large-scale experiment that CERN laboratory obviously is huge. Of course, experiment itself is coming from microscopic regions, but it's very expensive, unlike the labs that you could, the equipment that you could have in the labs and create materials. Very little control of the gauge fields that are basically generated by producing collisions. In tabletop experiments, that's of course relatively well, it depends. It depends, of course, how strong the magnetic fields you need. That's true. But if you're working with magnetic fields on the order of Teslas, which is not that difficult, all experiments with the graphene didn't need something that badly complicated. But yeah, I take it. It's not easy. Right. But it's not billions of dollars. I believe definitely not that much. And of course, not only the small size, essentially microscopic scales are pretty much the same in heavy ion collisions. The system exists very briefly, and of course those kind of things potentially could be circumvented in tabletop experiments on actual. So the question is, do you find that kind of relativistic physics and those types of chiral forms of matter? For that, you need massless Dirac-Weil fermions that are described by that kind of dispersion relation. That appears to be not a big deal. In fact, many materials have been discovered starting from about 2014 or something. And this is definitely not the complete list of papers. It was sort of the first few, and then a flood of the papers came out, and it turns out that those are much more common perhaps than we thought originally, or at least we didn't look for them as carefully. In fact, even some old-fashioned materials that have been around for a while, like this kind of alloy with some change of the concentration here, you could fine-tune to get essentially gapless excitations in the spectrum. The problem, of course, might be that it's hard to fine-tune, and then how stable it is until you start applying some additional conditions might be questionable. But in principle, what I'm trying to say that those materials in principle exist, and now the question is whether we can use them. So I'll probably have to go fast through this. I'll just skip. I just wanted to mention that we can have a wide range of parameters for those Dirac materials. Same for the Weil materials. There are different ways of verifying that we have exactly what I expect we have. So ARPA's experiments and measuring Fermi arcs in those materials kind of prove almost without doubt that we do have the materials which are Weil materials, where the Weil nodes are separated in the momentum space, or also in the momentum space and the energy going, one of them could be going slightly above the other. Since I'm going to talk about this kind of dispersion relation, of course, it's always kind of curious to understand it from the theoretical point of view. And since this is the lectures, this is a lecture, I was actually fascinated myself when I was looking at this, and I think many graduate students who are here probably would appreciate that this is a very beautiful piece of argument. When you have level crossings, and that's essentially what you need to create those gapless modes, you might naturally ask, do they actually cross or do they repel? sometimes if you consider some theories where the energy level cross, it's degenerate quantum mechanics or quantum field theory at that point, and you might think that it could produce a gap. Instead of basically crossing, as you naively think they should, they might be just repelling and creating gap in there. Well, it turns out that a generic two-band Hamiltonian could be written in this form. And of course, if you need to satisfy gapless condition, then in fact, the energy should be 0, means that B should be vanishing, and this stop going further for some reason. Oh, it says something here. Okay, so the bands are crossing when that condition is satisfied. In three-dimensional space, you could actually figure out that this condition can be satisfied always, because essentially you have 3 equations and 3 different control parameters, the actual momentum, and therefore you could always find the solutions to that. So in fact, they are not very rare to appear. Now, if you look carefully at that crossing, of course, no matter how the bands are crossing and what kind of complicated bands you are considering, you could always consider a momentum expansion around that point, essentially derivative expansion in coordinate space if you prefer, and keeping only the linear and the quadratic terms. Actually, wait a second, this is only the linear terms here in this relation. You will see that the first one here represents nothing else but just the tilting. So if you are not really interested in the effects associated with that, you could, in the first approximation, neglect that. And then if you consider the rest, you could analyze exactly how this works out and find that in general, you could introduce the proper basis, and essentially in that proper basis, it will be looking nothing else but like the wild Hamiltonian I just mentioned. And also you could introduce the concept of chirality by simply considering the sign, oops, sorry, wrong button, simply considering the sign of this determinant of the coefficients. So basically, this way you have an emergent concept of chirality, which is, of course, only true in the low energy description of the theory. So strictly speaking, in these models, chirality is not the property of the original Hamiltonian. Basically, you had finite bands. Those left-handed were connected to the right-handed branches of the dispersion relations. But in the sense of the low energy physics, they are the emergent chiralities, and therefore you could work with them approximately if only the low energy physics that matters here. Again, since this is a lecture, I couldn't resist to point out something that a lot of people mentioned, but nobody explicitly sort of showed it. You could write down explicitly the wave functions, and there are many different ways of writing that, of course. So this is one of the representations, and for the students, it's always good to reproduce this once in a while. You could consider the modification of the wave function on the small change of the momentum and see exactly how the wave function changes when you gradually change the parameter, the corresponding momentum in the momentum space. And you will find that approximately it's given by that phase. This is nothing else but the Berry connection that appears there, and of course that Berry connection gives you the definition of the Berry curvature that many people talked about in these lectures. And for that wave function I just had on the previous slide, if you do these calculations, which is essentially just taking some derivatives, you will find that this Berry curvature looks nothing else but like that. And of course, you don't have to go too much into the band structure or anything else. You just could remember your E&M introductory course, the Gauss's law, and you know that that is essentially similar to what you find in the coordinate space for the electrical field of a charge. And of course, you also know the Gauss's law, if you consider that kind of electrical field, you could integrate on the surface surrounding that region, and you will find how much of the charge sits at the inside of that sphere. So the same thing is here. If you integrate that out over any surface surrounding that point-like object at k equals 0, so we are talking about some object in a momentum space, you will find that it gives you non-zero value, and that non-zero value is plus or minus 1, depending on the chirality of the object. So basically, this is it. That's that Berry curvature that points to the topological origin of those particles, which essentially, from the point of view of dispersion relation, didn't look like anything super special, except that they were gapless. Now, of course, that has its own consequences, because unlike the momentum space that people work in high-energy physics, basically from negative to positive infinity, in solid-state physics, those bands are finite. And essentially, that means that if you consider one Brillouin zone, which is essentially then periodically repeated in all the directions, then you will see that if there are those lines of the Berry curvature coming of a certain point somewhere, from the topological point of view, they have to end somewhere else, because you could consider this Gauss's law and surround that region in a compact space. Surrounding that region means you could just divide it in the middle with that yellow line. That's really surrounding it, because it's a compact space. Yes?
That flux lines, physically what means?
Physically, they means that this is simply representing how the particles are essentially evolving when you change their momentum in the Brillouin zone. And you pretty much, when you change the type of the state, so you're basically looking at the states that exist in the Brillouin zone, and you characterize those states with this quantity. That's as much as pretty much needed.
In this case, is gapless?
Yes, at this point, that's the gapless mode, that's this dot, as well as that dot, because essentially what I'm going to just say the next one, that as soon as you have that chiral fermion with the positive chirality here, the field line, not the field lines, the Berry curvature lines should go, if they, let's see which way they start. So if this is positive chirality, the field lines go this way, and of course they have to end somewhere, because through that same area that is surrounding one of the nodes, it's essentially the same as a closing area around the other one, but with the opposite orientation of the surface. So if one of them is plus lambda, the other one has to be minus lambda, because you're integrating exactly the same field, but flipping the orientation of the surface. What is inside becomes outside, and what is outside becomes inside. And that's pretty much it. So essentially, this means that those chiral fermions, they must come in pairs. Or if they don't come in pairs, then in fact one of them would have the chirality 2 units of the charge, the other two will be 1 units of opposite charge. But total have to be 0. Anyway, this is some very famous no-go theorems where they always come in pairs and stuff like that. Anyway, one can very, very easily appreciate this with these very basic arguments. Of course, many people, when they're doing model studies, they're not really taking that complicated Brillouin structure in consideration, because, well, we were taught that when we are looking at low-energy physics, maybe we can go away with just considering low-energy Hamiltonian like that, and see what happens, do the predictions, and hopefully everything falls in place. There are several different ways to mimic the actual materials that you are considering with this basic model by introducing several parameters like those B0s and B vector, which I will be calling chiral shift. One of them, this one, is breaking the time invariance. It's representing the fact that the location of the two nodes in the momentum space, they are shifted with respect to each other. The other one is representing also a shift, but in the energy direction, so one of them is slightly higher than the other one. And of course, if those are 0, the two nodes coincide and you have a Dirac fermion, which is built out of two wild fermions coinciding at the same point in space. So this is the type of models that people often use to calculate many things. And there are a lot of different predictions of anomalous effects in semi-metals. So I will probably not go through everything. In fact, my goal is to show you a couple of examples of experimental evidence that supports those effects, like negative magnetoresistance, new types of collective modes, oops, wrong button, new types of collective modes, some anomalous thermoelectric effects, strain torsion-induced effects, and so many other things. Obviously, there are a lot of things that have been accumulated over the years, and some of these have been tested to a degree. The others are probably still an ongoing effort from the experimental point of view. So let me briefly tell you how those effects are verified in the experiments, and you will be the judge how convincing those arguments are. So the simplest one of this, and perhaps the first that more or less was accepted as an evidence of the chiral magnetic effect, is the negative magnetoresistance. So this is the general idea. If you have the electrical and magnetic field parallel to each other in some material, this looks like a two-dimensional, but it's not. It's just some material. And of course, when you have E dot B, then of course you will be generating chirality in the system, provided we have one of those Dirac wild semimetals. Somebody asked me in the previous lecture, how do you create N5? So that's pretty much a practical approach, how you do it. Of course, you have to take into account that there is this anomaly, and of course there is a finite lifetime or finite chirality flipping rate for those fermions, which, by the way, can be estimated for different materials. So in this steady state, uniform system means this is absent. Steady state means you reached maximum saturated N5 and it's not changing. This is pretty much the interplay between these two terms that will determine how much of chirality you are producing. That could be translated into this effective description using μ5. What is the equivalent chiral chemical potential, which is not that important for us at this point. Essentially, is determined by the susceptibility chi there. And of course, if the chiral magnetic effect current is present, then of course you have to induce this current proportional to the chiral chemical potential and the magnetic field. Substituting the value of this chiral chemical potential, you will find the result will be something like this. Of course, there is additional magnetic field sitting here. I didn't fully write it down. N5 is E dot B itself. So that's why instead of one B, you will get two different B's and E present there. And of course, that means that your conductivity, parallel component of the conductivity, is essentially this coefficient in front. And you see that it's a combination of the mean-free time for the diffusion or flipping of the chiral charge, and it's proportional to B squared. You could calculate the corresponding resistivity, and of course you will get the result something like that. And this has been tested in the experiments. So using that naive formula, you could pretty much fit the result with this upside down, well, it's not exactly parabola, bell-shaped form, and you will see that it fits the experimental data reasonably okay. There are a lot of different papers. Some of these results were accepted pretty much right away. Some of them were contested because of certain problems, some effects that I don't have time to discuss here. But in principle, it seems like a pretty reasonable fit to the experiment. The other type of measurements that have been done are related to this chiral charge pumping. On the theory side, the idea is that you are producing oscillating E dot B fields in the system by using some pump. So essentially, you use some laser field to send a pump to the system. You create chiral charge locally in that material. That chiral charge has some effect on the reflectivity of the signal if you send then a probe signal, because it changes the chiral charge density in the system, and therefore it modifies the conductivity, which in turn changes the reflectivity of the material. So very basic assumption. There is nothing super fancy about it. There is a specific setup that is done, and of course, on each of these pages, there are some references that are basically telling you from which experimental papers those came from, and this is the results they see. So they apply the pump and then the probe, and they see that after the pump was applied to the system, there is a delayed response in the conductivity, which is larger than the expected pre-pumped level. And in fact, that exists for a relatively long time, giving you the estimate of that chiral charge relaxation time, which could be in almost 100 of nanoseconds for certain types of materials. So this is essentially another way of testing that kind of works, and we indeed produce chiral charge, and in fact it exists for a relatively long time. So that's your chiral matter produced and exists temporarily. Finally, non-local anomalous transport, which is essentially the basic idea is that you have multi-terminal system where you are producing that chiral charge by applying electric and magnetic field in certain region, and then you see the probe of that effect chiral charge in some other set of terminals where your assumption is that the chiral charge, when it produced in certain region, that chiral charge is gradually diffusing, and of course if you are not too far, there will be a substantial amount of that. Further and further away, there will be less and less of it. So that's the idea. I didn't do anything. What happened? This is gone. Is it unplugged? Oops. Oh, good. So, is this thing now? Oh, it works. So basically, some experiments have been done on that, and of course, the measure that you are trying to consider is essentially this non-local resistivity over the local resistivity, and on the distance, how far you are away from the terminal that is producing this chiral charge. So there are all kinds of observables here. This is essentially also related to the same chiral charge diffusion rate. And of course, when you look at the dependence, indeed it fits this exponential decrease with the distance and fits the theoretical predictions that were given. So this is the snapshot of those at least 3 different, and by the way, this is not the complete list of observable types of data that exist. There are many others. The message here is that unlike in heavy ion physics, there is a relatively solid experimental evidence supporting that those anomalous chiral effects, they do exist. We can actually measure the observables related to it. But of course, there are many other predictions that may be even more interesting. I should actually mention that many of these observables are still indirect. If you think about all 3 of those possible observables, you could actually think of background effects as well, and you will appreciate the reason that you could think so easily of those background effects that, again, these observables are not exactly parity odd observables. I think something's... So one of the theoretical ideas that I was exploring myself is related to the so-called straintronics. The idea is actually very simple. When you have this, well, I should say without this A5, A50, if you have that low energy effective Hamiltonian, and then you look at the system and try to think where it came from. Well, basically, you could go at the microscopic level and see how the hopping between different sides of the lattice happen, find the low energy description of that, and it comes out automatically like that Hamiltonian with Weil or Dirac fermions. But then what happens if you strain the material, and there are many different ways of doing it, simply bending it or twisting it. And in fact, if those bending and twisting are small, you could actually see that the hopping parameters are slightly changing in certain ways. And if you re-derive the same effective theory, you will find that there are certain connections instead of this B, which was the shift between the two different nodes. There will be something else that depends on the strain. If you look at this B0, there will be something else that depends on the strain, and you could actually relate that to the stress tensor U, and you will see that all of those fields can be generated, and also they are technically fields that depend on space and time, because those deformations could be local. You could also introduce the corresponding pseudo-electromagnetic fields that are curl of A5 and the usual definition of E5, and indeed you will find that essentially they work like electric and magnetic field effectively. So these are emergent, they are not fundamental pseudo-electromagnetic fields. And from the physics point of view, it's very easy to understand what they do, right? It's essentially, if you have left-handed and right-handed particles, if you apply magnetic field, they are moving in the same direction. But now one of them is switching the direction because the charge becomes effectively proportional to that chirality in addition to the charge itself. Same for the electric field. So that's basically the bottom line, how they act. One of the interesting things is that if you twist, for example, a crystal like that, you could generate pretty much B5. There is a problem, however, with that. If you start looking at the low energy description of that theory, and you could introduce careful analysis, how all the low energy modes appear, in particular when those stresses are added, essentially it was in that Hamiltonian. You could write down the currents and charge densities present in the system and try to look what happens to your continuity equations. And this is when you get in trouble right away because, well, the first one is the continuity equation for the chiral charge. Who really cares? It's anomalous. It could be something on the right-hand side. You don't really pay attention to that. But then if you look at the second one, you should be alarmed immediately because that basically means that the local conservation of the electrical charge is violated. And literally violated in a local sense. There will be a charge moving out of here, and yet it will be not decreasing in value, or the charge will be decreasing, but there will be no current running out. And that, of course, will be really, really fundamental problem. In fact, how do you test this? Well, the way to test this is to consider some collective excitations and see what happens to them. And in fact, this is exactly what we did in one of the papers that we originally wrote. And then we realized that there is this problem, and basically all of that was garbage. Now, why is this garbage? Because, well, if you carefully start deriving those currents from the full theory, and in the full theory, I mean you take actually properly defined theory. Yeah.
Aware that there's a difference between the real electromagnetic field and the pseudo, in the sense that it changes between the different...
Yes, there is a huge difference between these fields.
There is no index for that. For the
no, the thing is that these fields are drastically different. From the origin point of view, they are emergent. They are simply driven by strains. The other one is true electromagnetic fields.
Yeah, but in the Hamiltonian originally?
That Hamiltonian is also sort of garbage because it's not completely capturing everything.
Yeah, because it depends on the value. I mean, the A will depend on the value. That's a huge difference when you treat currents.
Well, the thing is, I'm taking this as derived in the low energy theory. This is exactly what comes out.
Yeah, but in the values, the A change of sign.
Well, that's the A5.
This is just in one value.
This is in one value, but you need to take into account the other value.
That's true. That's true. But strictly speaking, it doesn't really matter because essentially for each of them, you will derive this. For each of them, you will derive this. In principle, you could have only these two modes, like in certain Dirac materials, and that's it. You could only have, but you're right, in principle, there could be additional cancellations. But the probability theories derived like this, they don't know about the other values. And of course, the only way to get them is to consider how they talk to each other. And the simplest model you could have is actually just a simple two-band model that is only one set of values like this and nothing. Perfectly well defined. If you consider carefully the derivation of the chiral kinetic theory from that original fundamental theory, I'll call it, even though it's simplistic, you will find actually that this is not the end of the story. In fact, this is indeed the only thing that comes from the low energy contributions of the particles if you limit yourself just to looking like through a lens only in the region of small energies. However, if you really start deriving the parameters of your low energy, if you start deriving those currents from the fundamental two-band theory, you will find that there are additional contributions that do not come from the low energy theory. They actually come from integrating out the whole band far below the low energy region. So if you wish, ultraviolet region. And of course, the explanation is perfectly the same as that very first model, one-dimensional model that Eduardo showed in his lecture, that essentially these two nodes actually talk to each other through that deep Dirac sea, which is deeply below the low energy region, but it's still in a finite band model captured perfectly. So, and these are the currents that you obtained from that derivation, and they perfectly compensate for all of those deficiencies in the theory. And one of the things you will immediately find that this will be 0 on the right-hand side as soon as you take those so-called Bardeen-Zumino, or if you wish, Chern-Simons terms into account. The anomalous Hall effect is perfectly reproduced if you take that into account. However, it also shows that there is absolutely no CME effect in equilibrium, precisely as required by the equilibrium theory. In fact, what it shows that, in fact, that mu5 that will be in the system, it has to be related directly to the chiral shift in the energy direction. And that precisely fixes basically all the deficiencies of the theory. And the main message is chiral kinetic theory that captures those chiral fermions in any kind of material. It only knows about the low energy physics. It knows nothing about the topology of the whole band structure, and you really need to include this. And in fact, that's the essential to reproduce all the physics correctly. Anyway, taking those into account, you might want to ask what kind of theoretical predictions you will find, prove that they're there, and everything's fine. So one of the things would be to consider some collective modes in the system. As I said previously, this was tried originally without those terms and the dispersion. And if you consider it correctly, and I'm not sure how well I'm doing on time, probably at least 10 minutes yet, right?
You have 8 minutes for the 10 to go.
Okay. So in order to consider that, of course, yes?
So when you consider the full band,
Yeah.
you showed those equations. Where's strain? Is there strain there?
Basically in B and B0.
Oh, you're including strain in B and B.
It's the complete zero, yeah. Wait a second, I should say that it doesn't really matter if you have strains or not in the band model. Basically, everything is captured by B, which could be space-time dependent. But this will become B0 plus A50. This will become AB plus A5B, and so on.
Doesn't the strain change? Okay. But the strain also changes the rest of the band structure, right?
Here it's basically minimal change. Basically, it will only essentially change the values of this B. Of course, if you get a nonlinear, everything's possible, yeah.
The main issue is you have to remember that the axial current is not conserved.
Right, that's true. But the thing is, naively, I had no problem with that, whatever that was, right? Actually, it is this that I had really big problem with.
No, there is no UV divergence. When you say this comes from the UV, I understand.
Yeah.
But there is no memory of any UV cutoff.
No, because generically, when these are derived, they're derived from the low energy chiral kinetic theory. It knows nothing about anything but infrared. Well, these do not have any dependence on the cutoff either. They are essentially topological in origin. So yes, we integrate over the energies far below the Fermi surface, but of course that doesn't appear explicitly anywhere. Absolutely right. Yeah, that is an important thing. It's kind of an indication that this is not a fluke. Coming back to the collective modes, of course, to analyze it properly, well, you have to consider how the E&M changes in the presence of those currents. You can consider the Faraday's law, which, of course, then you write in momentum space because you want to consider essentially something like a plane wave type of excitation or generically some wave type of excitation. Ampere-Maxwell's law contains this additional electrical field. So if you substitute in this equation the the magnetic field from the previous equation here, and then write down this expression in this form in momentum space, momentum energy space, I should say, because here there was also an omega that I divided the whole equation over that omega. And then in order to take the Gauss's law into account, of course, you have to see that the electrical field will be related to the local charge density. And of course, that's the two places where those anomalous contributions will contribute. So analyzing that equation, you could find the spectrum of collective excitations. And here we are considering Dirac, I should say while, in general, while semi-metal with non-zero chemical potentials present. And you will find that, of course, as usual, you will get plasmons. There is a splitting of the plasmons in the energy. There is one which is essentially longitudinal mode and two transverse mode. Essentially, you could think of those two transverse modes as left-handed and right-handed circularly polarized waves. The Langmuir frequency is more or less the standard quantity, except for this mu5 appearing here, changing mu squared to mu squared plus mu5 squared. And there will be all kinds of things there that you probably don't want to see, because I'm going to show this in a picture. And the picture shows that essentially there is this splitting between different modes, and the value, considering the magnetic field perpendicular to the chiral shift, or if you wish, the chiral shift perpendicular to the magnetic field is the only one present non-zero, and you will see that there will be a splitting in the energy of those two circularly polarized modes. So detecting that value of the splitting, of course, you could directly correlate that with the chiral shift present in the problem. And in this case, there are many other things, and of course, I don't have enough time to discuss all of that. But the full spectrum was analyzed under different types of conditions. And for example, one of the interesting predictions that you will find that if you take that crystal and twist it, in that semi-metal with non-zero chemical potential, you will find gas